Okay. So once everyone gets in here, we'll start talking about all of these different problems. So let's, this one. Okay. So in these problems, deciding whether they converge or diverge, the main tool um, is one of these comparison tests. And in both cases, how they work is you pick some comparison series. Some series which looks a lot like your series or has the same main parts as your series. And depending on whether your comparison series converges or diverges, you try to draw conclusions about the series that you started with. And so going through these arctangent of n over n, there are a couple choices that you can try to compare it to. One is this arctangent, and the other is this n in the denominator. So really, compared to the series arctangent of n or the series 1 over n. Those are kind of the two options here. Those are the two pieces. And one thing is that if you pick something to compare it to and you don't kind of get, or you figure out that it's not actually that good of a comparison, then you can try something else. So in this case, what turns out to be better is the 1 over n. That is good because, we'll go down to where we're actually starting to work on this. If we compare it to 1 over n, we know that that diverges. This is a series, so it's a p series because this exponent is 1, but also this is just a series we kind of explicitly analyzed, and we said that this series diverges. So how the limit comparison test goes is we take the terms from our original series, arctangent of n over n, and the terms from our comparison series, form a fraction and take a limit. And at this stage, there are no tests. There's just, here's a limit. We have to figure it out. In most of these series, since we're going to have two fractions, the first step is instead of dividing by a fraction, flip and multiply. We get some nice cancellation, and we get arctangent. And this is a limit that we can compute. This function has a horizontal tangent or horizontal asymptote of pi over 2. What you're really looking for here, and there are a bunch of different tests that have different numbers, kind of ranges you're looking for. In the limit comparison test, you want the limit to be anything but 0. So pi over 2, that works. And I somehow left out the conclusion here. But what we get to say is, by the limit comparison test, this line here says this is a good series to compare our original series to. This limit being a finite non-zero number says they're not the same, but they're kind of off by roughly a multiple of pi over 2. The idea is, in this series, arctangent is close to pi over 2, So this has a top close to pi over 2, this has a top of 1, and they're both dividing by n, so they're kind of off by this factor. So what we get to conclude is this limit says they're a good comparison. The series that we compared our original one to diverges. So we could just say the original series diverges too. So this pi over 2 on its own doesn't say that the series diverges. It's that this pi over 2 says whatever happened here, that's the conclusion that we want to draw. So in an example that I said in one of the breakout rooms was if you changed this n to n squared, then you could compare this to 1 over n squared. This series converges, and the limit you would make would be basically the same as the limit that we saw below. After cancellation, you would get arctangent, and that goes to pi over 2. So then you would say that since this series converges, this series also converges. So the limit comparison test isn't saying really converge or diverge, but it's saying whatever the one series does, the other series does too. Questions about that problem or that kind of a explanation of what we're looking for when we do the limit comparison test? Let me take a look at number 5 then. Oh, shoot. So in this 5, I made a mistake. So what we can really say, so let me go through 5. In here, these converges should be diverges, and the work really says diverges, but I wrote it down wrong, trying to do this too quickly. Okay, so number 5 here. This has, so there are 3 different ways that I'm doing this problem. In the first case, what we're looking for is we're going to do a direct comparison. And this is something which the inequality has to go just the right way, so sometimes it doesn't quite work the way you want it to. But in this case, what we can notice is this looks a lot like, or what you like to compare it to is 10 to the n over 6 to the n. That's a geometric series, and this minus 10, like this added constant, is really pretty insignificant when n is really big. So one way we can get that comparison is to say, okay, the bottom is 6 to the n minus 10. That's smaller than if it was just 6 to the n. If we flip both sides of this, so take the reciprocal, that changes the direction of the inequality. So 1 over 6 to the n is less than 1 over 6 to the n minus 10. And if we take this and multiply both sides by 10 to the n, multiplying by a positive number keeps the inequality the same way. So what we really get here is that our series is right here, and we're comparing it to this series, which is easier to deal with. So the red series here diverges because it's geometric. The R is this 10/6, and that has absolute value greater than 1. So what we get to say is that this series diverges and its terms are smaller than the terms of the series we're actually interested in. So if this thing's bigger than a series which already diverges, then the direct comparison test says that it also diverges. Okay. Questions about that one? Okay. To get to where there's a typo, you can also try this with the limit comparison test, which is this part right here. So again, you make kind of the same conclusion. It looks a lot like 10 to the n over 6 to the n, which you can write as 10/6 to the n. And like we said before, that's a mistake. This one diverges. So then doing the limit comparison test, we take the terms from the series we actually are interested in divided by the terms of the simpler thing we're comparing it to, flip and multiply, these 10 to the n's cancel. And so we get 6 to the n over 6 to the n minus 10. And here, one way to deal with this is an indeterminate form, so you can use L'Hopital's rule. The derivative of exponential functions is the exponential times this extra natural log. The derivative of a constant is 0, so what we get on the top and bottom is the same. Everything cancels and the limit is 1. So then what I did have correct was that this limit is 1, so the original series does the same thing as the comparison series. But where I was wrong was I mistakenly said that this series converged when it actually diverges because it's geometric. This series also diverges. Okay. So there's a question about, we get different answers, how do we know which one's right? The resolution is there's a typo. Every series should give you the same answer. Sometimes one series is able to get you an answer while another series isn't, or while another test isn't. But if two tests work, then they will always give you the same answer. Okay. And just to emphasize, there's another even faster way is this is also one where you can use the test for divergence. So in this case, the limit, we just take the limit of the terms that we're adding up. So we're looking at this series, just take the limit of this. We can again use L'Hopital's rule, grouping things. This is some number. It's a horrible number, but it's just a constant. And this is a geometric sequence. And if you start raising 10/6 to higher and higher powers, that goes to infinity. So maybe the fastest and most efficient way to do this problem is to notice the terms go to infinity, so the series is going to diverge by taking the test for divergence. This is also a good example because it shows that these two limits, or in both cases, you're taking a limit, but they're really different limits and you're using them in different ways. Here, this limit goes to 1, and that lets us draw a certain conclusion. Here, this limit is infinity, and that lets us draw a conclusion. So other than the fact that I messed up like the most important word in this problem, in the solution, are there any questions about this example? Okay. As long as we're kind of down here, let me do the last problem. So sine n plus 2 over n to the fourth. One kind of fact that you'll find out if you try it, but I'll tell you this is sort of what happens. The limit comparison test is tough to use with trig functions because when you take limits with trig functions, limits often don't exist. So for instance, if you tried the limit comparison test with the series 1 over n to the 4, what you would get when you take the limit you end up trying to take is you try to take the limit of sine n plus 2, and this limit doesn't exist. And if you get that the limit doesn't exist, you can't use the limit comparison test, at least not with that comparison series. So the limit comparison test isn't really a great test here. And with trig functions, it's often better to try to use a direct comparison because sort of squeeze theorem-like thinking, at least as far as the inequality goes, this trig function, you know you start with an inequality. Sine is always between 1 and -1. So adding 2 to everything, we get that sine of n plus 2 is between 1 and 3. And then the terms of this series we're looking at is between 1 over n to the 4th and 3 over n to the 4th. Now we really need to think about, so we have actually 2 inequalities here, and we need to think about which one is actually useful. And it turns out that this is the one that we want to use. Because this inequality says we're looking at the series with these terms. These terms are smaller than 3 over n to the 4th, and this series converges. Because it's a p-test, the p here is this 4, that's bigger than 1, so this thing converges. So then we say this series converges, our terms are smaller, and so we will also converge. What you don't want to do is to say, if you look at this inequality, then the series with these terms converges and we are bigger. That doesn't help because if you're bigger than a convergent series, you could go either way. So while there are 2 inequalities here, if we're talking since the series with either of these terms converges, we want to cite this inequality to use the direct comparison test. Questions about that problem? Let me jump back to number 2 here. So in number 2, we're trying to do a comparison. The idea is, what are sort of the big parts? In this series we're looking at, what are the really main terms as far as how big this sequence gets? And the 4 is a constant, so that doesn't do anything. And on the bottom, when you're comparing n and 3 to the n, 3 to the n is much bigger. So if you were to look at this series, these terms are really the ones that get the biggest much faster than the rest of it. And so those are the terms which really determine the behavior. This is also good that these are the terms which determine the behavior, because if you make a series out of these, that's geometric. And we can tell that since the R is 2/3, that's less than 1, this series converges. So the combination of, if we make a series of this, it's easy to deal with, and these are the big parts of the series we're originally given, those say that's a good comparison or a good choice for the comparison. We do still have to take the limit though. So the original series divided by the comparison series, we flip and multiply, the exponentials cancel, we get 4/n, and that's a 0. Now, in some cases, we can't draw a conclusion here. But if you look back at the section of notes where we said, in general, we want the limit to be not 0, but if it's 0, in some cases, you're able to make it work. How it works in this case is if the limit is 0, you're saying the top function is smaller, or the top series is, the top series is smaller. And so since this series on the top is smaller than the series on the bottom, and the bottom series already converges, then the limit comparison test gets us that the top series also converges. You can also do a direct comparison. So you can say dividing by n just makes things more complicated, and dividing by n makes you smaller. So if we weren't dividing by n, that is a bigger series, and we can already tell this is geometric, this series converges. So with even a little less work, I think you would still want to say this converges because it's geometric with absolute value of 2/3 less than 1. So you still want to make sure you provide enough justification for this, but we can do a direct comparison, which means we don't have to take the limit or kind of justify why the 0 limit still lets us draw a conclusion. Questions about this one? Number 3, I'll kind of skip over. Looking at the graphs, n is bigger, so flipping things, the inequality changes, and the series is bigger than a divergent series. So you can stick around if you have questions for that. But this next one, I want to make sure I talk about real quickly. We again are looking at the biggest terms, and what happens is the n squared is bigger than the 1, and this n to the 9/4, that has a bigger power than n. So we want to say, forget about everything else, but take these 2 biggest powers of n. If we use those to form a series, we get a p series, and since p is 1/4, that series diverges. And then setting up the limit like we did before, divide them, flip and multiply, and what happens, and this is what you should expect to happen if you have these powers of n around, is you end up with exactly the same power on the biggest, for the largest powers of n. And since those powers match, the limit is going to be 1, and since this isn't 0, the 2 series have the same behavior. So since this p series converges, the p series diverges, the original series also diverges. Okay. So sorry for holding you up a little bit. I can stick around if you have any questions or want me to talk about any more of these. The solutions are online if you just need to read through them a little more. But look out in the next 10 minutes or so for a quiz to be posted, and you'll have like an hour to work on it. And then upload your solutions. Okay. So I can stick around and talk some more, but if not, thanks for showing up. Hopefully the comparison tests make a little more sense, and I will see you guys not tomorrow because class is canceled for Piedmont Symposium.